All right. So next up, we're going to do an example that's going to look a lot simpler than the first one we did. And so we're going to try to evaluate this closed line integral of minus y dx plus x dy for this path. Here's x, here's y. That's like a circle with radius 1. And the path is going to move in this direction. Actually, I'll just put 1 right there. I think that's enough of an arrow to see. So it's moving this way. I'm actually going to highlight it in green because we've been doing that, and it will make it clearer that the portion right here is a part of the curve. So it's a closed curve, so we can use Stokes' theorem. Bad at highlighting. That's okay. Just going to accept that flawed line. Okay. So there's our curve C. And so I have a closed curve. If I think about trying to find a potential function for this, I would have like f equals yx, f equal xy. So I know that's not going to work. My curl, if I compute this, is not going to be 0. So I think Stokes' theorem is a good way to do this problem. I'm going to try to set up closed curve f dot dr is the same as f del cross f dot n ds. And I have to go ahead and identify all the different pieces of this. So my f is going to be minus y in the first component, x in the second component, and there's no z component, so I'll go ahead and write 0 there. And my curve C is given right here. And so I'll go ahead and pick my surface to just be the shaded in part of that circle. So my surface S is the shaded in part of that circle. And somebody gave me a picture for this problem, or they gave me like a series of points in a direction to connect them with a circle. So I don't actually have like a working equation for myself right here. I could go ahead and say this line is 1 minus x squared to get the edge of the circle. But that doesn't really tell me a z equals f of xy. And so this is going to be one of those examples where S is a flat thing, so it's very easy to go ahead and pick a unit vector without relying on all our formulas here. And the flat thing we've picked just lives in the xy plane. Oops. Oh, when I came back here, all my undos went away. That's okay. I'll just erase it. So if I'm thinking about curling my right hand around this curve, so you can kind of like put your right hand up against the screen and then curl it in a circle here, your thumb would come out the page this way. And so we know that the normal vector for this flat half circle is n equal to 0, 0, 1. And that's a unit vector. I've done that thing where I said if you pick your own unit vector because it's a flat thing, make sure it's a unit vector. It's not 0, 0, 10, it's 0, 0, 1, magnitude 1. Okay. So at this point, I'm kind of like, confused. I have my normal vector, but since I wrote it this way, I'm not really sure about how to set up my ds. So I'm going to go ahead and compute my del cross f and see what happens. And so I'm not going to do the crossing out part because I feel like probably really good at cross products at this point. So for the I hat component, I'm going to have d dy of 0 gives me 0, minus d dz of x gives me 0. It's like a fun face. Minus j hat is d dx of 0, 0, minus d dz of minus y is 0. Plus k hat, oops, gives me d dx of x is 1, minus d dy of minus y gives me minus 1, so plus 1. Let me just check that. 1, minus 1, plus 1. Okay, so I've got 0, 0, 2 here. So my integral C f dot dr is a double integral of del cross f dotted with n integrated over the surface's area. So I'm looking at a double integral of 0, 0, 2 dotted with 0, 0, 1 integrated over the surface's area. That's an integral of 2. That's 0 plus 0 plus 2 over the surface's area. So I'm just looking at 2 times the double integral over the surface's area, which I don't need to set up a complicated like bounds of integration problem to do this because I know that the area of half a circle is 1/2 times pi r squared. So 1/2 pi r equals 1 squared. This is just going to give me pi. If I really wanted to set it up, I could do 0 to 1 r dr d theta. Theta goes from 0 to pi. Or I could set it up minus 1 to 1, 0 to root 1 minus x squared, dy dx. These will all get us to the same place. But this one's easier. And so do I have enough time to do this? Yes, I do. Okay, great. So this type of problem where your normal vector is like in a single direction because your surface is flat is actually a Green's theorem problem. So you can always remember the Stokes theorem formula like this and do your curl and it will cancel out all except one component. But if you don't mind committing like the meaning of a new thing to memory, then you could always write down this instead, which is that Green's theorem is going to tell us that the integral over a closed curve of some function m dx plus n dy is going to be the double integral over the area. Oops, should do r of partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. And this really is the same thing as we did before, except for that we said f was m n 0, and then we took the curl to get that thing dotted with n. And the thing is that if you commit Green's theorem to memory, it's only going to work for things that are 2D in the xy plane. Whereas if you remember this process, it's going to work for things that are 2D that lie in the xy plane or the yz plane or the xz plane. So I really don't recommend remembering Green's theorem, but you can do it if that makes you happy. And here's a picture. So you are going to have to always remember that C is oriented this way for greens. That's because it uses the positive normal vector that had to follow from the right-hand rule. So, and this is our region R. So go ahead and write that down if you want it. We will keep on doing more examples right after this.